Good afternoon, ladies and gentlemen, and it's a pleasure to be talking before you today. Apologies that I wasn't able to make it over to be with you in Las Vegas. I had some work commitments, and that prevented it. My talk today, as Will has said, is about chemometrics with Perl and pharmaceutical applications. Because my background originally is I trained as a pharmacist in the United Kingdom, so I still do research and development work on pharmaceuticals and spectroscopic analysis, which requires pattern recognition and machine learning algorithms, which we tend to call chemometrics. It's the chemical data analysis is called chemometrics. So the contents of my talk today then is to briefly go over what's called vibrational spectroscopy. So that is the spectroscopy, the interaction of electromagnetic radiation with the bonds in molecules, principally organic molecules, and that interaction leading to absorption of energy by the electron cloud that causes the bond to start vibrating. The different types of vibrational transitions that can occur depending on the energy of the photons, so the vibrational energy level transitions. There's not a continuous distribution of transitions because it's quantum, it's based on quantum mechanics. It's sort of discrete energy levels between the different transitions. Near-infrared spectroscopy is the spectroscopic method of analysis that I principally use, but I also can use things like Raman spectroscopy. And then I will cover some basic chemometrics, a qualitative analysis, which is the mathematical model to identify something from its spectrum, and then some pharmaceutical applications of near-infrared spectroscopy. Before I launch into the major part of the presentation, there's quite a few sort of definitions that it's worth getting out of the way. So I'll be talking about active pharmaceutical ingredient. That is the actual drug substance that is within the pharmaceutical matrix, such as a tablet or a capsule. There are other fillers and ingredients that are called excipients, and typically only a small part of the actual finished dosage form, the drug, the dosage form, tablet or capsule, is actually drug. IR is infrared. DLP MEMS is digital light processing, micro electromechanical systems. So that is the little handheld spectrometer that I'm going to show you a slide of. Originally comes from Texas Instruments. It's Texas Instruments technology, but it is now produced as a functioning spectrometer by a Taiwanese electronic manufacturer called InnoSpectra. And that's the device that I'll be using, but it's based on the DLP MEMS system. EMSC is a type of data processing for NIR spectra. It's called it's extended multiplicative signal correction. GUI, everybody will know that's graphical user interface. InGas is the type of semiconductor that responds to near-infrared radiations. It's indium, gallium arsenide. Multiplicative scatter correction is another type of data processing of spectra before actually identifying with the chemometric model. NIR is near-infrared. PCA stands for principal components analysis, and it's a data reduction technique that maps a multivariate signal, so a signal with lots of different variables. It transforms that signal down as a vector in a low-dimensional pattern space, so it can be plotted as a point in an n-dimensional pattern space, and that can be used for cluster analysis, which is what I've done in the example that I'm presenting in this talk. I'm not showing a quantitative method today, but if you are interested in doing quantitative analysis by NIR spectroscopy, typically you would use a quantification algorithm called partial least squares regression, PLSR. PTFE, polytetrafluoroethylene, is the white reflectance standard that's non-absorbing, that's used typically in near-infrared spectroscopy. So it's small particles of PTFE powder, which are compacted together and held together under heat. They're sintered together to give what's called a diffusely reflecting surface, so that light is reflected diffusely, so that it can be used as a reflectance standard to standardize the instrument. R is reflectance. Savitsky-Golay, or SG as I've got here, is a type of smoothing and differentiation filter that can be applied. So it's a type of digital signal processing that can be used to remove noise from a spectrum, which is called smoothing, but also to resolve overlapped absorptions by using what's called the second derivative. So the rate of change, where you have overlapped absorptions will typically resolve them and give you something a little bit more like a traditional mid-infrared spectrum, which and those typically have nicely resolved absorption peaks. SNV, standard normal variate, is another scatter correction algorithm that's used on NIR spectra to remove the effects of scatter. And T-squared is Hotelling distance, and that is the statistics that is used in principal component analysis for measuring the distance between scores. And from that, one can work out whether something belongs to a given class or cluster based on that multivariate distance. It's equivalent to the multivariate equivalent to the t-test. So many of today's methods of instrumental chemical analysis that acquire multiple measurements of chemical substances, and often at many hundreds or thousands of variables per measurement. In the case of near-infrared spectroscopy, the variable is actually the wavelength in nanometers, but it can be in infrared. It can be what's called wave number, or in Raman spectroscopy, it's wave number shift from the actual laser line. So this generally gives too much information for people to be able to properly interpret spectra by eye in the past, or things like UV ultraviolet spectra. You can look at a single wavelength and potentially set up a calibration curve to calibrate the spectra to give you the concentration of an analyte in a solution. But it's generally not possible to do that really now with these sort of multivariate modern methods of analysis. And so it requires really the use of fast personal computers to generally get the most out of the spectra, to process them. And the good thing is that as near-infrared spectroscopy has evolved as a analytical technology, so have personal computers, and also the pattern recognition and machine learning algorithms to get the most out of the data. So they've kind of gone hand in hand together. It goes back though quite a long way. NIR spectroscopy was discovered in 1800 by the German-British astronomer William Herschel as the invisible form of heat energy that was in sunlight. When he dispersed that from light coming from behind a curtain, it was detected as beyond the sort of red end of the light. So he couldn't see it, but he used thermometers to actually detect that there was radiation there. And it was largely left ignored until probably like the 1960s, because a lot of analytical chemists thought it was the kind of junkyard of the electromagnetic spectrum. Absorptions were overlapped, they were low intensity, there weren't the sophisticated algorithms to properly model the data and get anything useful out of it. So it was left largely ignored until probably like the 1960s, I think. So moving on to the theory, near-infrared vibrations arise due to the absorption of higher energy photons that match the ground state to what's called the first, second, and third overtone energy level transitions. So these are higher frequency than the transitions involved in traditional mid-infrared spectroscopy. And this puts the NIR region at about 780 to 2,500 nanometers. Because these absorptions, they're technically forbidden by quantum mechanics, because they involve transitions from the V equals 0 to the V equals 2 and 3 levels, and quantum mechanics says the vibrational quantum number should only change by plus or minus 1, I think. So they're not. This type of spectroscopy is not supposed to occur according to theory, but it does. But because the photons, the energy of the photons is so high, there tends to be not that many of them around. So the technique tends to have low molar absorptivity, and this is quite a benefit for the technology, because it means you can analyze samples often without having to do any sample preparation. So you don't have to dilute them down with an oil, like in mid-infrared spectroscopy. You could potentially put a tablet straight onto a glass window, shine some light into the tablet, and measure the light that is reflected back, and that forms the spectrum, and that can be done within a few seconds. The spectroscopy that I've been doing here and presenting on, mostly the spectra take about 8.3 seconds to acquire. And from that, you can work out what potentially work out what a product is made of, or how much of a particular analyte, such as the drug, is actually present in the sample. So, and that can be done within about 8 seconds. And there's a lot of benefits there compared with traditional wet chemical analysis, like HPLC, high performance liquid chromatography, where you have to grind samples down, dissolve them into particular organic solvents, pass them through a column, record the sort of ultraviolet absorption as a function of the time it takes for these things to elute off the HPLC column. And that's very time consuming, and it requires lots of organic solvents and things. So this technique potentially can be calibrated by techniques. It's a secondary analytical technique in the most cases. It can actually be calibrated with data from a reference laboratory wet chemical analysis, and then it can be used alone without having to do all the wet chemical analysis. And that could save a lot of time and a lot of money on manpower time and things like the solvents and raw materials that you require to do wet chemical testing. So it has a lot of benefits. The chemical bonds that we tend to see in the near-infrared region generally include a hydrogen atom, which is covalently bonded to a heavier atom, and that's typically carbon, oxygen, and nitrogen. And the NIR diffuse reflection spectra typically have overlapping absorption bands and non-linear baselines. So the baselines tend to be not horizontal across the wavelength range, from the short wavelength to the longer wavelength range. There tends to be a sort of curvilinear or feature with increasing absorbance across the wavelength range, and those effects, that's generally down to scatter. So the light interacts with the particles, and it basically penetrates beneath the surface of the sample and undergoes multiple scattering from different particles that the photons meet. Sometimes the photon gets absorbed, other times it carries on and hits something else, etc. So you get these multiple scatter, and that typically, and it's wavelength dependent, so it causes this curved baseline. Generally, we have to remove the curved baseline before we make the mathematical model. So this slide here just shows the vibrational transitions involved. This is the textbook potential energy, and then the distance between the bond, which is going to be like a carbon and a hydrogen, or an oxygen hydrogen, or a nitrogen hydrogen. And you can see the V, the ground state here, naught. Then we have 1, which is the mid-infrared, the fundamental vibration frequency. and near infrared is this V0 to V2 or 3. So these are the first and second overtone vibrations. There's also one higher up there, which is the third overtone as well. So that happens as well. NIR vibrations typically involve two things happening. Bonds either stretch, as shown here, so it can be a symmetric stretching here, where the internuclear distances between these bonds both stretch the same amount, so it's symmetric. Or you can have a sort of a compression and a stretch, so it'll be an asymmetric stretch. And then there's these four various modes of bending, where the actual angle of the bond can also change as well, instead of actually stretching. So these are the different vibrations that can be that occur within the near infrared region. For data pre-processing, to remove the, and I will show a slide with some NIR spectra on, but because those baselines tend to be curved, there are different mathematical algorithms applied to remove the curvature. So we have what's called detrending, involves fitting a quadratic polynomial and subtracting that away. So that removes a curve, or the standard normal variate transform, which is similar to multiplicative scatter correction, and then the more recent extended multiplicative scatter correction. There's also the Savitsky-Golay family of smoothing and differentiation filters. So a zero order smooth, which will just take out some of the noise. A first order Savitsky-Golay, which will take out some of the noise. It will take out some of the the baseline offset where the spectrum hits the y-axis, and it will also remove, because it's rate of change, it will remove a linear trend from the spectrum as well. Moving to the second derivative removes quadratic effects from the spectra, and also resolves overlapped absorption peaks. Moving on now, so that was the fun bit, the theory. Moving on to the aim of this. The aim of the work that I've done was to automate the generation of scripts in a mathematics programming language called GNU Octave, which is similar to MATLAB. Because I have a toolbox of chemometric algorithms, and I didn't see any point regenerating all those in Perl. So I used Perl to actually generate lots of different mathematical models and do batch modeling of the spectroscopic data to allow, and this allows me to do quantitative and qualitative methods, spectroscopic methods of analyte determination or analyte or product identification, respectively. So Perl controls Octave for me, and generates, in some cases, 100 or 200 different models, and captures the key metrics, the key statistics that allows me to rapidly identify the optimum model, or the near optimum, can then use for identification or quantitation. And then the second part of the work then was to have a graphical user interface developed in the Perl TK for control of the handheld spectrometer that I'm going to show a slide of. Acquire the background spectrum of the PTFE, the white PTFE standard, which is the non-absorbing diffusely reflecting reflection standard that's used in NIR, and then basically acquire the spectrum, process the spectrum, and allow interpretation of the spectrum to give an identification or quantification of the spectrum, using a model developed in Octave, one of the models developed. So an example I'm going to show is the pharmaceutical application. It's a qualitative method, and it's identification of a tablet called Cialis or Cialis, 20 milligram tablets. It's just something that I have some samples of. And this is just a very simple example of a near-infrared method to identify a product, and the method was quickly validated using near-infrared spectra of Viagra tablets. Now they are the same; it's the same therapeutic class as Cialis, but the active ingredient is obviously different, and the excipients, so the other ingredients that are present with the drug, they are different as well. So this is just to illustrate the method. It's not the not a particularly fantastic identification. It's just simply for illustration purposes. So Cialis itself contains the active pharmaceutical ingredient called tadalafil. So here is just a 3D molecule that I pulled off the net. I've plotted this in JMOL, and just to show you, you can see the grey atoms represent the carbon, the white atoms represent hydrogen. So we've got lots of CH molecules here, which are likely to show absorptions in the near infrared. We've also got nitrogen, hydrogen as well here, so an NH. So that's also going to be or should be active in the near infrared region as well. So we should get interesting spectra. The DLP MEMS spectrometer that InnoSpectra produces this small device. It's about the size of a desktop mouse. It's really quite portable. It can be used with a Bluetooth low energy connection to a smartphone, but I've developed software that works via a wired USB connection, USB 2 connection. So you can see lights here that show you whether it's Bluetooth active, etc. And we've got here a sapphire glass window. Sapphire glass is a very tough glass, and it's sort of transparent to near infrared radiation. So it's quite a useful optical window. Put the sample on the top here, and inside here there are two tungsten halogen lamps, 0.71 watts each, and they produce energy which is that falls within the near infrared region. So it's a good light source for NIR spectroscopy. So the sample goes on the top here, which could be a tablet, or it could be a glass vial with powder in, or something else. And the device is actually wired up to PC, and the PC or the graphical interface can then trigger the lights to switch on and measure the light that is reflected back from the sample. So the light penetrates into the sample, undergoes diffuse reflectance, and some of it then emerges back, and inside is the in-gas detector, which picks up on the energies at the different wavelengths, and the micro mirror device, the Texas Instruments digital micro mirror device, it produces the spectrum by switching different mirrors on and off. It can do that in a few different modes as well. There's a linear mode where it'll do that in a straight line, mirrors on and off, and that will sort of scan through a particular spectrum, or it can do a type of a Fourier type of Fourier transform called a Hadamard transform. But in this case, I think I've just stuck with I think the linear mode, because I think that's recommended by Texas Instruments. So the instrumentation then is the InnoSpectra DLP MEMS handheld spectrometer, which is known as, the model is NIRSG1. It has a standard, a 1 millimeter standard indium gallium arsenide mixture detector, which is uncooled. Hence the upper wavelength range is about 1700 nanometers, and it's 1.8 millimeters by 0.025 millimeters slit. It's got the two 0.7 watt tungsten filament lamps set beneath a sapphire glass window, and I think these typically would have a life expectancy of around about 1,000 hours or so. So it should last quite a long time before those lamps need replacing. They're not user replaceable. The spectral response is typical in-gas, uncooled in-gas range, about 900 to 1700 nanometers, and it produces quite a respectable number of wavelengths as well. So the optical resolution is quite good for such a small device, about the size of a desktop mouse. It's 228 wavelengths, and that's quite. I think that's quite good. There are a lot of there are other handheld devices out there that have around about 100 wavelengths. So this is quite a high resolution, I think. As I said, there's different modes that you can run that run the spectrometer in terms of measuring the wavelengths and the energy at each wavelength. So linear, Hadamard, and slew scan, and I've stuck with I think the linear scan mode. I've had my spectrometer hooked up to my desktop PC, which is an Intel NUC 8th gen, I think, quad-core CPU with a 8 threads running at 2.8 gigahertz. It's more than capable of running the device. Doesn't need a particularly powerful PC for that. And I use the Ubuntu Linux 20.04 as well. So here's an example of the graphical user interface that I produced in Perl. So it's basically got two windows. This first window here pops up initially, and a lot of things are grayed out until the first thing is done, which is a scan has to be acquired of the reflectance standard, because the background spectrum that you get in near-infrared spectroscopy depends on things like the temperature of the air and the amount of humidity in it, and that can change in a room or a lab quite quickly over the course of a few minutes or an hour or so, and that will change the sensitivity of the device, because moisture in the air absorbs, etc. So it's necessary to measure a background scan first. And I've set the GUI to not permit anything to be done until a background scan has been measured at least once in a 24-hour period. And here you can see the background reference spectrum, spectrum of a tablet here matching Cialis, 10 milligram tablets. Another example scan here, pseudoephedrine hydrochloride 60 milligram tablet, so that's a decongestant tablet. And we have here, so this is the scan window. So the first time this is used in a 24-hour period, scan would be grayed out, but reference wouldn't be. It would be the only option that could be triggered. You'd have to put the sintered PTFE block on top of the optical window and measure this and acquire a background spectrum before it's possible to then put a tablet or a capsule on the window and measure the spectrum. And here's the spectrum of the pseudoephedrine tablet. This is raw absorbance. So you can see here the baseline is not flat here. It kind of curves up like here. And superimposed on top of that curvature are some overlapped absorption peaks. So the chemometrics that I've applied to this very simple example that I'm going to be showing is what's called the standard normal variate transform of the absorbance spectra. Because the spectra that I will show you, you will see that they fall into two groups for each product, and that is because the light reflects off the tablets in different ways if the markings are different on each surface of the tablet for a given product. And in this case, both products have debossed markings on both sides. So product identification marks are stamped into the tablet, and that affects the reflection of the light in particular ways, causing two groupings of spectra per product, and that isn't useful for identification purposes. It's not a useful form of spectral variance, so that has to be minimized before moving on to the chemometric model itself, which is based on principal components analysis. And here I've just used a very simple two principal component model. So this is the multivariate sort of mapping of the spectrum from the original high dimensional space of 228 wavelengths down into a pattern space of just two variables, which is something you can plot essentially on a graph. It isn't necessary. I must stress, though, it's not necessary when the device is actually running to ever plot anything. The maths can all be done on the PC without having to show principal component scores plots. These are just these are nice things to have to illustrate things for people and put them in journal articles or presentations like this. But the maths doesn't. You don't actually have to show the actual maths to the end user. So the scores vectors then, which are the multivariate mapping down into the low dimensional space, these scores vectors are used for identification, and the distance in the pattern space that is used in order to identify or reject a scores vector from a model is called Hotelling's t-squared distance. So typically what this does is it will measure the distance for scores vectors, which are points in that reduced dimensional space. It'll measure the distance that encompasses 95% of the scores of a particular class of substance, and draw an ellipse or in 2 dimensions, or a hyperellipsoid if it's more than 2 dimensions, and anything that falls outside that sort of critical distance, that probability ellipse, would be rejected and would be considered not a member of the class. So the model is based on spectra of Silas 20 milligram tablets, and you'll see in some of in a slide that there is a red ellipse with red dots inside, and those red dots represent the spectral projections of spectra of Silas. And you'll see sitting quite a distance away from that ellipse are blue dots, which are the spectral projections into the score space of the Viagra spectra. And so the Viagra spectra are correctly rejected as not belonging to the class Silas 20 milligrams. So here are some NIR spectra of both Silas, which is shown in red, and Viagra 100 milligram tablets here shown in blue. So subplot A and C represent the original absorbance spectra, and you can see you get two classes of two groupings of spectra in Silas, and the same in Viagra. And that is because as I say, the debossed markings are different on both surfaces for each product. So by performing what's called the standard normal variant correction, that you get subplot B and subplot D, and you can see the spectra now overlay much better, so that the unuseful variance between the spectra has been eliminated largely by performing an SNV. And it's now, with the SNV data, it's now possible to produce the qualitative model based on PCA. So the PCA model, this shows the scores plot, principal component 1, which is the major source of variance in the spectra. These are abstract. These are abstract sort of factors which are produced by essentially singular value decomposition. So that the first principal component dimension captures the major source of variance, which is really the distance between. You can see here the two groups of spectra. PC2 captures the next major source of variance, and these are orthogonal, so they are uncorrelated sort of factors. So we can plot them. We can plot these two in Cartesian coordinates here. So you can see here the red ellipse represents the critical value for alpha equals 0.05. So the type 1 error here would be 5%. So 95% of the spectral scores for Silas should fall within this ellipse. And you can see the Viagra fall outside the ellipse, so they are correctly rejected. So their Hotelling's, the distance, under the Hotelling's distance is measured from the origin, from the centroid of the cluster. So this distance here, therefore, would be, these distances to the blue dots are significant at the p less than 0.05 level. So Perl then has been quite successful for allowing me to produce lots of different chemometric models, and I use this for other work that I'm doing. I have a study that I'm ongoing with Oxford University in the UK, where I have done some work looking at quantifying the levels of antimicrobials and antibiotics in tablets, and developing NIR methods to quantify the level of antibiotics, irrespective of the actual matrix composition. So which is quite a new development. And so I use it for that as well. I can generate hundreds and hundreds of models quite quickly, allowing me to do other things while the data processing is going on. And then once those models are produced, they can be saved as a text file that has all the key chemometrics things in it, such as the singular value decomposition, the scores vectors from PCA, the mean spectrum, standard deviation spectrum, etc., the critical values, etc. And those can be loaded in by the Perl TK GUI that I've produced. So the Perl GUI can read those files. It can also control the spectrometer, trigger the reference spectrum acquisition, and then process the spectra with whatever scatter correction algorithm is required, and then do the apply a qualification or quantification algorithm onto the transformed spectrum to give either an identification pass-fail, or to give a quantification of the particular analyte level. So in this case, also I put here this method could be repeated the other way around. You could produce a model for Viagra, and and then sort of validate it with the Silas spectra. But it's been quite useful for me in my work. So I'm quite impressed with Perl. I like the syntax. I've been using it for over 20 years, and I have no intention of moving over to that other language that seems to be quite popular, which I don't like the look of the syntax on. I don't know if I'm allowed to say that. Well, I'm not going to mention the name of the other programming language.
Thank you very much.
You can work that one out. Okay. So I'd just like to end by giving some acknowledgements. I'd like to thank the following individuals: Will Braswell, who is the founder at also Parallel Technologies Inc. and CTO at Events Medical Software LLC. Brett Strad, independent contract Perl programmer at Acutis Computing and Data Consultancy LLC. Dr. Mark Perry, who's been our reviewer of abstracts and our submitted articles. We've produced little papers on our presentations as well, and Mark's been very good in doing all the reviewing, I think. All other members of the Science Perl Committee I'd like to thank as well, plus the Perl and Raku conference organisers. And thank you for your time.
Wonderful. Thank you, Dr. O'Neill. Okay, we have 4 minutes for questions. 4 minutes. Yes, George.
It sounds like these sort of things would radically reduce the cost of establishing things like
Come on up here, George. Come on up here, buddy. You have to speak into this and be close enough for him to hear you.
Okay, got it.
I'm all the way over in the UK, so it's a little bit.
Just about there and then speak.
Okay. So is my understanding correct that it sounds like this could radically reduce the time and cost it takes to establish things like the accurate expiry conditions for a particular medication?
Potentially, yes. If the actual the drug, do you mean expiration as in terms of the amount of drug substance present?
Yes.
Or, yeah, I mean, if the drug substance is degrading quite rapidly, then yes, you could potentially use this technology. Yes, yeah, and it's not the good thing about this little handheld is the performance is quite good. A benchtop near-infrared system will typically cost about probably $60,000, and this device is a few thousand. So I mean, there's also there's the savings in terms of technology, but then there's the saving again in moving to this handheld device versus a benchtop. And so there's potentially multiple kind of levels of savings.
Other questions? I've got one. So I wonder if it would be possible for some device-toting authority figures to utilize this for detecting verified versus counterfeit drugs, maybe in a drug raid or in a government inspection or a health and safety inspection, or is that a far-fetched idea, or is that within the realm of possibility?
No, that's not far-fetched. I think that's very much within the realm of possibility. Basically, all it requires is models produced of the genuine substance before those inspectors would go into a facility. And as long as they've got models that they've validated of the genuine products, then they could take the counterfeit versions. And if the spectra come out significantly different, then yeah, they've got a very useful device that it's handheld. It can be carried around in a very small case. So I think that's distinctly possible.
So there's a lot of field applications.
I think so. Yes. Yeah.
Okay, great. 30 seconds for anyone else. Last call. Okay, thank you very much, Dr. O'Neill from the UK. All right, check out his new paper in the Science Perl Journal. Thanks, Doc. We'll catch you next time.
Thank you very much, Will. Thank you all. Thank you. Goodbye.